Hello, good morning from Assam. I hope everyone is keeping fine during the COVID-19 pandemic situation. During these tough times, let us not forget the sacrifice and hardship undertaken by the health workers across the globe. Today is the 9th of the International Virtual Workshop on Global Seismology and Tectonics, and we are shortly going to witness the 11th lecture of the series from none other than Professor Andrew Michael from USGS. The virtual workshop commences with his lecture entitled Why It Is Hard to Count Earthquakes, Estimating Earthquake Completeness. And we are blessed to listen to the second talk from him today. Quite incidentally, he was the first from USGS to represent lecture in this virtual workshop and also the last to represent USGS. It is hugely overwhelming and motivating to see a person of his stature delivering 2 lectures in this virtual workshop. I would like to especially thank and acknowledge his profound spirit. The title of Professor Michael's lecture today is The Poisson Assumption Applications in Spite of Clustering. In this session, we have with us Professor J.R. Kyle, former Deputy Director General of Geological Survey of India as the session chairperson, Professor Ramesh Singh from Chapman University, USA as the chief guest, and Dr. Saurabh Barua, chief scientist from CSIR NIST, Jorhat as a session chairperson. May I request our session chairperson, Professor J.R. Kyle, for his initial remarks. About Professor J.R. Kyle.
Thank you, Santanu. Thank you so much. I think, yes, as you said, during this difficult situation, you are not leaving us to learn. So there is no end of learning. And I think this workshop started with Dr. Michael. And today also we have got an opportunity to listen to him again. Dr. Michael, you actually opened the eyes of not only to the young researchers, but all of us, that catalog is a catalog. It's not a data. I think that was a very important message in your last lecture. And people plot anything and everything to show the statisticity map. And very cautiously you have informed us that don't take it as data. You try to understand what you are doing. So it was wonderful, Michael, and today also you are also going to cover a very important topic on Poisson applications. So we look forward to listening to you. Thank you so much and welcome again to this platform. Thank you so much for being with us. Over to Shantanu, please.
Thank you very much, sir, for your initial remarks. Professor Ramesh Singh, he will be online after a short while. Now may I request our session co-chairperson, Dr. Saurabh Barua, for his words. Thank you. About Dr. Saurabh Barua.
Honorable Professor J.R. Kayal, our guest of honor today's lecture, Professor Andrew Michael, Professor Ramesh Singh, and the convener of the session, Dr. Shantanu Barua, and all dear participants. This is the second lecture by Professor Andrew Michael, and we are really honored to have him here in this platform on this international seminar. We were enlightened through his lectures on how to estimate the true seismological database, which is the prime concern for every seismologist to proceed forward with earthquake seismology aspects research. So he will touch upon a very important topic today on Poisson's ratio, which will no doubt indeed will be the prime input for again the same aspect what we are discussing over last 2 days, the seismic hazard assessment. So without wasting much time, I request Professor Andrew Michael to proceed forward. And before that, I hand over the platform to Dr. Shantanu. Thank you so much.
Thank you very much, sir, for your kind words. I have introduced Professor Andrew Michael to everyone on day one. However, for a person with towering caliber and credentials, I would any day love to do it again. Professor Michael has been a geophysicist with the US Geological Survey's Earthquake Science Center in Menlo Park since 1986, where he combines observations of earthquake processes and statistical models to determine long-term and short-term earthquake probabilities, to evaluate proposed earthquake prediction methods, and to better understand how stress and structure function as part of his seismologic processes. His present activities includes works on the USGS earthquake probabilities and occurrence project, the induced seismicity project, the working group of California earthquake probabilities, and is a member of the National Earthquake Prediction Evaluation Council. He pursued graduation from the prestigious MIT in 1981 and master's in 1983 from another prestigious institute, Stanford University. From the same university, he pursued and completed his PhD in the year 1986. He has authored more than 100 papers and reports, including publication in renowned journals such as Science, Nature Geoscience, Journal of Geophysical Research, etc. He was the editor-in-chief of the Bulletin of Seismological Society of America from 2004 to 2010, served on the Society's Board of Directors from 2014 to 2019, and was its president from 2017 to 2018. In 2011, for that work, he received the Society's Distinguished Service Award. For his career contributions, he was given the Department of the Interior's Distinguished Service Award in 2019. I will end it here. The space is all yours, Professor Michael. Thanks again. Over to Professor Michael.
Thank you, Shantanu. I appreciate the kind words, and I'm actually very glad to give a second lecture, and I have to emphasize that while preparing this lecture, it gave me a chance to learn some more about the Poisson distribution, particularly also how it's derived, and this came about actually through a mistake that a subtle mistake that a colleague made in computing some earthquake probabilities that helped me learn more, and I'm happy to share that with you today. So with that, I'll share my screen and start presenting the talk. Okay, so as I said, people have said the lecture is about the Poisson assumption, and that we're going to use it despite the fact that earthquakes are clustered. So Simone Denis Poisson, and my French pronunciation is lousy, so I will mispronounce his name or pronounce it in multiple ways throughout the lecture. He was a phenomenal mathematician and physicist who is known for many things. And in seismology, for a long time, the thing he was known best for was Poisson's ratio, the elastic behavior of solids. And most rocks are Poisson solids. And I would say from the beginning of BSSA in 1911 through the 60s, almost every mention of him was about the Poisson's ratio and a Poisson solid and wave propagation. And that changed as we became more statistical, and we started discussing frequently the Poisson process and the distribution. And I just want to acknowledge that he had many other contributions to science that we will not have a chance to touch on today. So what is a Poisson process and a Poisson distribution? So the process is a point process. So like an earthquake is a point in time and a point in space. Now, clearly an earthquake takes a little bit of time and it takes up some length of the fault, but we will think of it as a point. And we assume these points happen randomly. They occur at a constant rate and they're independent of each other. And sometimes this will be referred to as a completely random process. So one thing about a Poisson process is no matter how long you have to wait for the next event, has nothing to do with how long it has been since the previous event. So If you say, well, it's been 10 years since the previous event, that gives you no information than if it had been 1 year. So if it is a Poisson process, it limits predictability. The Poisson distribution expresses the probability of how many earthquakes or events could occur in a fixed interval of time, say a month, a year, a decade, and or space, some given area, if the earthquakes are governed by a Poisson process. So the process is sort of the fundamental thing, and the distribution is the math that goes along with it. So can we recognize a Poisson process? So here we have 9 sets of simulated events. So their time goes in dimensionless units from 0 to 100. And we have different behaviors. These down at the bottom here come from a process that's clustered. And then up at the top, here we have an anti-clustered process. And these events are avoiding each other. Each stick is an event. And somewhere in the middle is a random process, a Poisson process. And it's sort of hard to tell. I think a lot of people, when they look at this, they think, well, maybe up around here, this looks random. But actually, I'm going to tell you right off the bat that number 5 is the Poisson process. And you can see that it has clusters and it has gaps. And this is a good reminder that a random process does not look like this top one, almost evenly spaced. It can be a very clustered looking process, even though there is fundamentally no clustering. This, of course, is down here where we have lots of earthquakes at one time and then a big long gap. This is what a real clustered process looks like. Okay, just as it emphasizes this point, now each of the 9 models are all drawn from a Poisson process. Each line has the same number of earthquakes, but yet the character is different. Some of them look fairly maybe like the previous one. Some of them have some big clusters and gaps. This one has big gaps and some very dense clusters. So it is a random process, and so it is variable. It doesn't always look the same. So in seismology, the first mention we know of the Poisson distribution and process was from K. Aki in 1956. I have to admit, I've only seen a reference to this paper. I haven't seen it itself. Sanford and Holmes in 1962 looked at some micro-earthquakes in New Mexico in the United States and showed that the micro-earthquakes were not Poissonian, that they were clustered. And then Leon Napov in 1964 wrote an algorithm of declustering, and he wanted to remove the aftershocks and produce a Poisson sequence of earthquakes, but he failed to do it. And he concluded that earthquakes, even without aftershocks, are linked. And he cited the paper by K. Aki as being similar for large earthquakes. He may not have been right about this, but I think it's important to emphasize, in 1964, there was no declustering mechanism that produced anything looking like a Poisson process for the earthquakes that were left behind. Then a very important paper, Alan Cornell in BSSA in 1968, and this is really in many of our minds the seminal paper on probabilistic seismic hazard analysis. And he used the Poisson distribution for earthquake occurrence. But note that he had no tool in 1968 to decluster a catalog. And in fact, in that paper, as I'll talk later, he never mentions the idea of declustering an earthquake catalog. And then another landmark paper, Gardner and Napov wrote a paper in which the title was, "Is the sequence of earthquakes in Southern California with aftershocks removed Poissonian?" The abstract was a single word, yes. So in between the 10 years from 1964 to 1974, Napov, now with Gardner, managed to produce a declustering method that has become heavily used. Okay, so the Poisson process. Let's talk about it in space. So the points are located randomly on a mathematical space and are independent of each other. So let's see, does that describe earthquakes on the globe? Of course not. As we all know, many earthquakes, these are magnitude 7.5s in over 100 years, are clustered around the Pacific Ocean on the what's called the Circle of Fire, and in other very active regions such as here where India is colliding to the north. So okay, earthquakes are very badly described as a Poisson process in space, but let's think about them in time. Okay, so again, if it to be in independent time, points are independent and randomly occur at a constant rate. So here we have the number of earthquakes per month. That's on the vertical axis from 0 to 200 a month. These are magnitude 4 and greater from 1950 through 2006. And we can see that there are many spikes. And on the top of every one of these spikes is an earthquake marked by a star that is magnitude 6 or greater. So what does this tell us? This tells us that we have spikes when we have big earthquakes. We have aftershock sequences. So earthquakes are not independent of each other. And actually, they're not occurring at a constant rate. So, okay, truly earthquakes are not Poissonian in either space or time, but yet we still make a lot of use of this distribution. Of course, here's an aftershock sequence just to drive this point home. I think I showed this plot in my first talk. The main shock is here. This is a magnitude time plot for the first week. And you can see the rate of earthquakes is decreasing through the first week. If we then zoom in, the first week is now here, and we look at the first year, the rate continues to decrease. The rate is changing with time. It is not constant, and it is related to the main shock. The earthquakes are not independent. Okay, so that's why earthquakes cluster. They have aftershocks. Here's why earthquakes may avoid each other. And it's that plate motions build up stress, which must be released. And this is a nice animation we show for public lectures. There is a fault, and someone has built a fence across the fault to keep their cow in. And cows will be a bit of a theme at times in this lecture. With time, the plate motions try to move the fault, and they bend the fence until finally, in an earthquake, the fence breaks and the fault slips, and the cow seems to be very undisturbed. Cows are really often very placid animals, so this is very realistic. And then the whole thing goes back again, we think, in an earthquake cycle, at least roughly, because the plate motions continue. And of course, this is not actually just hypothetical. There are real fences in California built across faults that are then offset by earthquakes. So as an example of this, this is Parkfield, California, home of cows and maybe non-Poissonian repeating earthquakes. So you may have heard of Parkfield. It's a very important experiment that the USGS ran and I worked on early in my career. This is our small office, our field office here. Another geophysicist who happens to be my wife, and some cows and a fence. This is not crossing the San Andreas Fault. The office is near the fault. So Parkfield is here in Central California. It is just north of the 1857 Fort Tejon earthquake, which is sort of the Southern California big one. Then the 1906 Northern California big earthquake is here. There's a creeping section of the fault that doesn't produce large earthquakes, and then Parkfield seems to produce a lot of magnitude 6 earthquakes. So are the Parkfield main shocks a cyclic non-random sequence? So there were Parkfield about magnitude 6 earthquakes in 1857, 1881, 1901, 1922, 1934, 1966, and 2004. What we plot here is the time between successive earthquakes and then a cumulative distribution. So there are no earthquakes that have times between 0 and 10 or 11 years. Then at 12 years, we have the time between the 1922 and 1934 earthquakes. Then here we have right at 20 years. This is 1881 to 1901. And we just build up what we call an interevent distribution. And then we can try to see what sort of behavior this shows. So it seems to fit fairly well with a log normal distribution. A log normal interevent times are often used to model times between repeating earthquakes due to elastic rebound. What log normal means that if we took the logs of the time, so the log of 12, the log of 20, those log of the interevent times would have a normal distribution. So it looks like it fits pretty well. Earthquakes seem to be somewhat cyclical here, and therefore time varying probabilities are valid. There's a little bit of predictability. If they were instead exponential, we would expect if they were random and Poissonian, we would expect the interevent times to fit an exponential distribution like this. And clearly it looks more like the blue line. So, and we can actually reject the exponential distribution with 98% confidence. So it looks like here the earthquakes aren't random, they are somewhat repeating, also not Poissonian. But yet we will go ahead and keep using the Poisson distribution. So the first thing I want to do is derive the Poisson distribution. And we're going to do this from the binomial distribution. It's going to take me 4 slides. This is the first of 4 slides. And we're going to do this despite the fact that I've just shown you that earthquakes don't behave like this. And of course, that makes the Earth more interesting. But yet we need to learn about the Poisson distribution. So let's imagine that we observe earthquakes for 10 years. And during that time, we observe 5 magnitude 5 and greater earthquakes. So therefore, there's the rate is 5 earthquakes in 10 years. Or if we wanted to study earthquakes in a single year, we would normalize that to 0.5 earthquakes in a year. And we want to answer the question, what is the probability of 1 earthquake occurring in 1 year? So what we'll do is we'll imagine the year as a bin with P equals 0.5 chances of an earthquake. And the bin, the year-long bin, can only have 0 earthquakes or 1 earthquakes. So the probability of 0 earthquakes is 0.5. The probability of 1 earthquake is 0.5. So the possible outcomes over here in the diagram with 1 bin is either one possibility is that there's 0 earthquakes, and the other possibility is there's 1 earthquake. It's a coin flip, 50-50 chance, and the probability of 1 earthquake is 0.5. So these are binomial probabilities. They are limited, and they are wrong for earthquakes. Why are they limited? Well, what's the probability of 2 earthquakes in a year? We can't do it with this single bin. Okay, so now we're going to go to what is the probability of 2 earthquakes in a year. And so we're going to need 2 bins. So we'll divide the year into 2 halves, each with a probability of having an earthquake of 25%, probability of no earthquake was 75%. So possible outcomes. We could have no earthquake in either bin. We could have 1 in the second bin. That would give us an earthquake. We could have 1 in the first bin and none in the second bin. That would also give us 1 earthquake. Or we could have 1 in each bin for 2 earthquakes. Probability of this is very simply 0.75 squared. The probability of one of these 2 things happening is the probability of 0.75 times 0.25 plus the same thing again, so 0.375. So now notice the probability of 1 earthquake happening is now 0.375. On the last slide, it was 0.5. So it's changing, so something's wrong here. And the probability of 2 earthquakes would just be, the probability of this happening would be 0.25 squared, a fairly small number. So the probability of 1 earthquake has changed, so something is bothersome. And what is the probability of 3 earthquakes? So we still can't do that. Binomial is limited. Okay, so now we're going to go, of course, to 3 bins. So we have 3 bins. Each bin has a probability of having an earthquake of 0.5 divided by 3, 0.17. And 1 minus that for the probability of no earthquakes is 0.83. There's only one way to have 3 bins and 0 earthquakes. And we would take 0.83 to the third. The probability of that happening is 0.578, almost 0.6. There's also only one way to have 3 bins and 3 earthquakes. And the probability of that will be changed. Instead of 0.83, now we have 0.17. So a very small number, 0.17 cubed, is a small probability. It gets more complicated if we want to have 3 possible outcomes of having 3 bins and 1 earthquake. So this is sort of 1 earthquake in each of 4-month periods. We can have it in the first 4 months, we can have it in the second 4 months and zeros elsewhere, or we can have it in the third 4 months of the year with zeros elsewhere. So the probability of having 1 event in these 3 bins is there are 3 ways to do it, and each one of these 3 ways, each line is a row is a way, has the same probability, 0.17 times 0.83 squared for about 0.347. Probability, as again, of 1 event has changed less than last time from 2 bins to 3 bins, and it changed from 1 bin to 2 bins. And finally, possible outcomes with 3 bins and 2 earthquakes is almost the same. There's 3 ways to do this. So we multiply 3 ways times now we square the 0.17 because we have 2 bins with 1 earthquake times 0.83. We only have 1 bin with 0 earthquakes, and we get another probability. So we're not going to go to 4 bins. Don't worry. This is enough bins. But what I want to point out is the critical thing in here is how we calculate the number of ways there is to do something. So if you know some combinatorics, the number of ways to have k earthquakes in n bins when each bin can only have a 0 or a 1 is the combination of n things taken k at a time. And the notation for a combination of n things taken k at a time is these parentheses with the numbers with no line. This is not a fraction. My first paper I ever published with combinations in them The typesetter put a lot of lines in between and turned all my combinations into fractions. It was very difficult to get fixed. And the equation for n things k at a time is n factorial over k factorial times n minus k factorial. And if we work that through for 3 things taken 2 at a time, we can work it through and we get the number 3 just like we got here. So this works. But what we need to remember is this formula here, just this part here. Okay, finally, we'll get to the Poisson distribution by the second half of the slide, which is currently blank. So if the rate of earthquakes is lambda, and we have n bins, then each bin has a probability of 1 event equal to lambda over n, and each bin has a probability of 0 events of 1 minus p. And we're going to compute the probability of k earthquakes. So this is the binomial probability of k earthquakes in n bins with p probability in each bin. This is the number of waves, the combination of n things k at a time. This is the probability of the events that the bins that had 1 earthquake in them, so it's p to the k. This is the probability of the bins that had 0 earthquakes in them, so it's 1 minus p to the n minus k, what's left over. And this is what we can do for binomial probability, and we can do this for as many bins as we want. So what we're going to do is we're going to increase the bins, so n goes to infinity. In this case, p, which is lambda over n, will go to 0. And the limit of the binomial probability distribution under these conditions with n going to infinity is the Poisson distribution. I am not going to derive this at this point. Andrew Chamberlain, a mathematician, has a very nice write-up on this. I made a short thing, tinyurl.com/binom-Poisson. And what you get in the end when you take the limit of the equation off on the left, you get this equation here. The probability of k events occurring is equal to lambda to the k times e to the minus lambda over k factorial. And this is a very handy formula. This is what you should use when you want to produce the probabilities of 1 earthquake a year. And actually, if lambda equals 0.5, then the probabilities in 1 unit of time, a year, is 0 earthquakes is 0.6, 1 earthquake is 0.303, 2 gives like here, and 3 earthquakes goes like that. And if we could go to 4 or 5, we could go as many earthquakes as we want. And all of these values are different from the previous 3 slides. So that's the message. You should always use this Poisson distribution to calculate the number of earthquakes that are happening when the earthquakes are behaving like a Poisson distribution, which of course, as I pointed out earlier, they don't. So let's look at some properties of the process and the distribution. So the events are independent of each other. They occur at a constant positive rate. And of course, we can only have integers. We can't have half an earthquake. We only have whole earthquakes. We look at this distribution. It has some interesting properties. The mean of the distribution is lambda. The variance is the lambda. And for high, if lambda is high, it becomes approximately a Gaussian with a mean of lambda and a standard deviation of lambda to the half, the square root of lambda. And you can sort of see that here we have black dots showing the probability of different numbers of events. And we have the different number of events on the x-axis. And here, if we follow the black dots for lambda equals 5, it's sort of a skewed distribution. It doesn't really look normal. But if we go up, say, to lambda equals 15, it starts looking a lot like a normal distribution. But remember something here. The normal distribution is defined on real numbers, and the Gaussian distribution and the Poisson distribution is only defined on integers. So it's not really the same thing. And that's why I don't draw lines between these triangles or squares or dots, is because this is not something that is a continuous distribution. It's only defined in integers. So this is what we had over here before. Sometimes we also like to have the probability of k or fewer earthquakes happening. This is the cumulative distribution. We just do a sum over the previous equation. And we get these sort of sigmoidal shapes. And just be familiar, if you see a sigmoidal shape of the number of earthquakes smaller than some number versus a number, that also sort of looks like a Poisson distribution. You'll see plots that look like this later in the talk, so sort of training your eye. Finally, we won't derive this, that the time between earthquakes, what we call the inter-event distribution for a Poisson process, is exponential. And this has a very exciting and sort of counterintuitive result. The most common, the most likely inter-event times are short. So the probability density function for inter-event times, probability of inter-event time t, time between earthquakes, is equal to lambda e to the minus lambda t. The mean inter-event time is 1 over lambda. So if we have lambda equals 5, then the mean time between events is 0.2, 1 over 5. And notice that this equation here, this is a maximum when t equals 0. The time between events is 0. And so that's what we see here. At 0 inter-event time, these functions are maximums. And for high rates, they're very concentrated down near short inter-event times. Earthquakes happen close together. For higher rates, they're spread out a bit more. But of course, later in the talk, what we'll actually see are inter-event distributions plotted as cumulative distribution functions, which is this distribution here, 1 minus e to the minus lambda t. This is the distribution of inter-event times shorter than some time t. And again, the mean is still 1 over lambda. But anyway, if we do these sort of, this is sort of like the curve we saw in the plot of Parkfield for random behavior, where it goes up steeply at first, and then it flattens out. And of course, what we know when we look at cumulative distributions is that when we see that they're very steep, that means there's lots of the mass of the distribution in this area. And then there's less probability out here where it gets flatter. This is the last property I will talk about, the probability of one or more events. This is often used in forecasts. So we want to say, well, in the next week in this aftershock sequence, the probability of there's probability of 1 or more magnitude 5 earthquakes. So the probability of more than one event is equal to 1 minus the probability of 0 events. The probability of k events is this. So therefore, the probability of k greater than or equal to 1 is 1 minus the probability of 0 events. In this case, we will define, the factorial of 0 is 1, lambda to the 0 is 1, so we get 1 minus e to the minus lambda. This is a handy little thing. If you know the rate of earthquakes in some time window, you can say what's the probability of at least one of them. So here is in red is the probability of 1 or more events as the red line, and then this line is just probability equals rate. So here we have rates. Rates can be greater than 1, but probabilities on the vertical axis can only be no higher than 1. The probability can't be against 1, so of course it has to roll over and go asymptotic to 1. Note that this line is a very bad approximation to the red curve for high probabilities and high rates. But as we get to small rates, the two merge very well. And in general, for small rates, when the lambda is less than 0.1, the probability of k greater than or equal to 1 is approximately the rate. So this is sort of a convenient thing. If someone tells you, well, the rate is 0.05, you can say, well, the probability that I'm going to have at least one earthquake is also 0.05. It's close enough. Okay, so now how do we test for Poisson behavior? This is if we have a data set and we've declustered it and we want to know whether it really fits a Poisson model, how do we figure that out? And so as I said before, when we show these to people, they may say they think it's in the middle because they figure I probably put the right answer in the middle, or they would tend mostly to put it a little high. But how can we actually test this? And it's hard to test it in this form. So one thing we tend to do for testing for Poisson behavior is we tend to produce plots of inter-event times. So here's the time between earthquakes. And let me just go back a slide. So we're actually, in this case, looking at the times between earthquakes for this first row here, down on the bottom, which is very clustered. So there's a lot of short, it's clustered. So we see, it's clustered models, we see a lot of short inter-event times. And then notice the thing goes flatter, so we see fewer long inter-event times. So again, where things are steep in cumulative distributions, that's a lot of earthquakes. When it gets flatter, it's fewer. And then if I do my best fitting exponential to this, it doesn't fit very well. We can see there's big gaps, systematic gaps here and here. And so now I'm going to do this for all 9 of those models. And so while it's hard to look at just those stick plots, we can see very clearly this one doesn't fit well. This one still fits better, but not as well. And if we keep going, the one in the middle fits really quite well. It's pretty good. And that is the one that was actually drawn from a Poisson process. And then as we go to anti-clustered processes, like let's look at model 8, you see now we have fewer short inner event times than the exponential predicts, and more longer inner event times. So actually they're sort of more in this middle area. It sort of catches up and goes above. So this sort of plot is actually very diagnostic of a Poisson process, but it's not enough information. So here we have some earthquakes. So we have 1,000 periods of time. This is fake. And we have 1,000 earthquakes. And I will tell you that I made this up with exponentially distributed inner event times. So I know what it is. And I know that there's no relationship between successive inner event times. So here are the 2 tests we have to do. The first is the one I already showed you. Cumulative number versus inner event time. The black is the data from the previous plot, which is just from a random number distribution. And you can see that the red curve follows it very accurately, which is the best fitting exponential. And if we do a KS test, a Kolmogorov-Smirnov test, which tests whether or not the data, the black line, could be drawn from the red distribution, we get a very high probability that the black data has an 80% chance that it could be drawn from that red distribution. So it looks like it fits a Poisson process. The other test we do is we check the autocorrelation function of the data. So autocorrelation function measures the relationship between inner event times separated by lags. So this is at 0, we have the question, is one inner event time related to itself? Well, of course. If I take the time between the second and the third earthquake and I compare it to the time between the second and the third earthquake, they're identical. And so we get an autocorrelation with 0 lag of 1. This is always true. But notice if we look at now the second inner event time to the second to third earthquake time to the third and fourth earthquake time, that would be a lag of 1. And we look at all the different lags of 1. We see that there's very little autocorrelation. And the blue lines are 95% confidence on a single value. And we can see that almost all of them, except for 0, fall below that. Here's one that falls above it. But, you know, out of over 20 things, you're going to get one that falls above 95% confidence. So both of these together tell me I have Poissonian data. So now I'm going to take the same inner event times, but I'm going to sort them. And so now what this does is it means that at the beginning, when all the inner event times are small, and I'm adding them together to get the time to the earthquakes, there's a lot of earthquakes happening, and then it slows down. So think about this. If I sort the time, so it's an increasing sequence, then there's going to be some relationship between successive times. So now let's look at my 2 tests. So this one is identical to before, literally identical if they're the same exponential inner event times. And it tells me that this could be drawn from a Poisson distribution. But now, because the inner event times were sorted and it was artificially done, notice that there's a lot of autocorrelation between successive inner event times. So even though this one makes me think it could be Poissonian, this one tells me there's no way this is Poissonian. This is way less Poissonian looking than a real aftershock sequence, but this autocorrelation function test tells you something about aftershock sequences. Because in an aftershock sequence, when we start having a lot of earthquakes, we have short inner event times, and that continues. We continue to have short inner event times. Let's look at the opposite case. Now we have random times. Now they're log normal times. So these are the sort of times that are often used to model repeating earthquakes. And again, log normal means the logs of the inner event times have a normal distribution. We like the log normal because it means all the e to the logs will be greater than 0. And in the earthquakes, of course, the inner event times have to be positive. The next earthquake has to happen in the future. So that's one reason we like log normal distributions. And in this case, first we'll look down here at the autocorrelation function, and we see that there's very little autocorrelation. We see a little pop-up here for some reason randomly But again, when we have many things, some of them will be above 95% confidence. It's very telling that the early ones are very small. But now the KS test is a very bad fit, and actually the probability that the data was drawn from the exponential distribution is incredibly small, which is good because it wasn't. And so really what I'm showing you is that to truly, this also tells me now that this is not a Poisson process. So to tell us whether or not we have a Poisson process really requires two tests. There's really quite a number of other tests that have been developed for this problem in papers by Peter Shearer and Phil Stark, or in Proceedings of the National Academy of Sciences and other authors. But it's a complicated thing, and you really need, often one test will not tell you enough information. So both tests are needed to determine if the data shows Poisson behavior. To end this section, I'll show you an example. This is a global catalog of data from 1900 to 2010. I was looking at whether or not earthquakes around the world were random or not. And at magnitude 7 and greater, if I don't decluster the catalog, we see that the KS test tells me that the data are not Poissonian. This p-value is much less than 0.05, which would be 95% confidence. And you can see that there's too many short earthquakes. Even at magnitude 7 and greater, we pick up the fact that there are aftershocks. The autocorrelation function test, however, didn't show anything. So that tells me that really, for in this data set, most of the time when there was an aftershock, there was really only one magnitude 7 or greater. There weren't a lot of magnitude 7 or greater aftershocks. If we decluster the catalog, and this was using a modified Gardner-Knaupoff declustering, when we'll discuss declustering next, then we find that the fit is much better. The KS test gives a value above 0.17, and the autocorrelation function is also still greater than 0.05. And so once we decluster the data, it looks like globally the earthquakes were actually randomly distributed in time. Not in space, just in time. Okay, so now we know how to test whether we're going to if we've satisfied the Poisson assumption with some data. So if the seismicity is not a Poisson process, which we showed at the beginning, and we want to model it that way, we have three choices. One, we can pretend it's Poissonian. That can be very dangerous. Sometimes you can get away with it, but it can be dangerous. A second choice is we can decluster the catalog, and that means we get rid of the foreshocks and the aftershocks, and then we can test it and see. And there's another third choice that I will not discuss today, which is we can transform the time. We can warp the time dimension into a new dimension in which the seismicity appears to be Poissonian. This is done with ETOS models. Just know it exists. I don't have time today. Okay, so declustering. So 1974 Gardner-Knaupoff paper. This paper is very important because it's used, this method is used almost ubiquitously, very, very frequently for probabilistic seismic hazard assessment. So what they did was they said, okay, here's a main shock, and based on its magnitude, we will draw a circle around it, and everything inside this circle for some period of time will be called an aftershock. I show those in blue, and this earthquake which shows up outside, well, that's another main shock. The problem is the spatial circles are too small for large earthquakes. And the reason for this is they based all of this on data in Southern California in 1974. Southern California doesn't have magnitude 9 earthquakes. And so the largest earthquake they had was like a 7.3 in their data set. So here if we have magnitude and we have the lengths, the distances of earthquakes, this is the distances of their circles, we can see that even the largest circles get only up to about 100 kilometers or so. This red line is the empirical lengths of faults for earthquakes, and we can see that once we get up to magnitude 8, the length of a fault, and therefore the length of the aftershock region at a minimum, is much larger than here. So this needs some correction for large earthquakes. And I'm also going to show this is for magnitude, this is the length of the aftershock sequence. And even for magnitude 9s, they only gave a length of about 4 years. And now we'll look at magnitude 6.7 here, maybe a length of not quite 3 years, 2.5 years. These are too short. Let me show you they're too short. Here we have the Northridge aftershocks. Again, I showed you before that you could see them slowing down even for the first year. And actually, you can see them slowing down for at least 7 years or so. And so Gardner-Knaupoff would say the aftershock sequence is over here. This is, again, too short. It's definitely too short for very large earthquakes. This is a very famous earthquake for aftershock statistics. It was magnitude 8.25 in Japan, in Nobi, Japan in 1891. This is a large earthquake, and it happens to happen in an area where there aren't many earthquakes. And so Omori, of course, of the Omori relationship, started tracking the number of felt earthquakes in the region. And he did this for about almost 20 years following the earthquake, and he showed that they fit this line. This is log number of earthquakes versus log time. So the Omori relationship is a straight line here. And then what's truly amazing is the open circles were added by Utsu in 1969. So all the data, here's 1900 here, all the data from 1900 on were added to this plot after Omori had made it back at about 1900. And it was still decaying like an Omori sequence. So aftershocks can last a long time. So Gardner-Knopf declustering is very heavily used in probabilistic seismic hazard analysis. And one good thing for them is it keeps the biggest earthquakes and those produce the most hazard. It has some problems though. One thing is it adjusts the B-value of the catalog. Let's assume that a catalog has a B-value of 1 with all the earthquakes in it. In each aftershock sequence, we're going to keep the biggest event and remove all the small ones. So now we have fewer smaller events and we lower the B-value. I'm also going to notice that in the original paper, Gardner-Knopf invited users to try different window definitions, but very few of us have done that. I did it in my global study to get longer windows, and recently another researcher did that in Oklahoma to get better windows. But very often we just use these default windows that Gardner-Knopf defined based on Southern California. So here's what this does to the B-values. So this is the full catalog of global earthquakes from 1982 to 2011 over 5.5. It's a complete catalog. You can see it's a very straight line. Even in the, remember, the triangles are the bins, and this is the cumulative distribution, number of events versus magnitude. This is a Gutenberg-Richter plot, and we get a B-value of 1. And if we decluster it, I go from 12,000 events to about 6,000 events. And instead of B equals 1, we get B equals 0.9. And notice that it crosses. If I were to forecast large earthquakes using this B equals 0.9 from the declustered catalog, I actually start getting more earthquakes than were in the full catalog and were predicted by the full catalog. So the lowering B can be a problem when you're trying to forecast the rate of large earthquakes for seismic hazard analysis. There are some other choices. Reisenberg in 1985 made a declustering method, and instead of basing the cluster shape and duration just on the largest event, using these circles with predefined size and durations, his goal was to define clusters by letting them grow. So what happens if two earthquakes are close together, then they glue together, and very slowly you can build a cluster up from the connections between the small earthquakes. His time definition was based on Omori's law. His space definition between two small earthquakes was based on the source size of earthquakes. And links between smaller events can hold a cluster together. And this also method keeps the biggest events, and users also rarely change the parameters. But it's more organic. It lets the cluster sort of define itself instead of being predefined the way Gardner-Knopf did. Another more recent method, the nearest neighbor method by Zhaliapin et al. In 2008. What they did was they measured sort of a rescaled time between the nearest neighbor events, so the two events, any event and its nearest neighbor, and also a rescaled distance. And these scalings are complicated and have to do with fractal dimensions and relative weighting of space and time. And what they find on this rescaled time and magnitude and distance plot is it's bimodal. And so the earthquakes that are essentially far from each other in time and space, those are the independent events. And these are the aftershocks here that are clustered together. This is sort of a log of the nearest neighbor distance in both space and time. And you can see it has sort of two Gaussians, a multimodal Gaussian. And we can sort of split this yellow line, which becomes this yellow line in this other space. And then we can say, okay, all the earthquakes that are in pairs up here, we'll keep those, we're going to throw out the rest. So this is some sort of Reisenberg-like, because we're looking at the distances between small earthquakes. It has slightly different behavior. And finally, there's ETOS declustering. Now, I'm sure that Nicholas talked about the ETOS method a lot. So in ETOS, the total rate of earthquakes in time and space, X and Y are space, is a background rate that's constant in time. So that's a Poisson model, plus some contribution of the triggering of all the previous earthquakes. This is summed over all the previous earthquakes. So it has a Mori decay and a spatial kernel and the productivity of how many aftershocks we expect. So we have a background rate and a triggering rate. We add them together to get the ETOS rate. The probability that an event is an independent background event, so this is this probability of the event J, is equal to the background rate at that location divided by the total rate from ETOS at that location and at its time. And what happens here is we sort of randomly keep events based on this probability. If this probability is very high, then we're likely to keep the event. If the probability is low, then it's likely to be an aftershock and we probably throw it out. But it is a stochastic process. If we do it twice, we won't get exactly the same answer. And we don't necessarily keep the largest events, so this actually tends to not bias the b-value. Finally, a declustering method that we just published, Andrea Lenos and I just published it this year. We call it Robert. It's very much like stochastic ETOS declustering. So the name Robert, I made up. I thought it sounded nice. Andrea put up with it. Regionally optimized background earthquake rates from ETOS. So to regionally optimize, when we take a catalog, we determine parameters by fitting an ETOS model to the regional catalog, and we also compute the uncertainty. And for 1,000 iterations, we draw parameters, ETOS parameters from the distributions estimated in the previous step, and then we do stochastic ETOS declustering applied to the observed catalog, and we produce 1,000 declustered catalogs. Which each of those declustered catalogs, we spatially smooth it the same way we often do in seismic hazard analysis for smooth seismicity. And then we average the 1,000 to produce an A grid, an earthquake rate grid, which is used as input to PSHA. The thing here is this is the number of earthquakes in a given declustered catalog. This is a cumulative distribution. If we used Gardner-Knopfloff, we would get only 100 earthquakes in this catalog, this particular one. Reisenberg gives many more. Nearest neighbors here. The ETOS, if I use the best fitting ETOS parameters, we would get a little over 300 earthquakes. But with Robert, what we actually do is we get a distribution of numbers. And I think this is very important in seismic hazard assessment to try to incorporate uncertainty. So if we apply all these methods, this is looking at the effect of declustering on earthquake rates in the San Francisco Bay Area. This is from 2013 to 2018. So here's the full catalog. You can see some aftershock sequences. But actually, this is an aftershock sequence. This is actually a swarm. And Gardner-Knopfloff gets rid of a lot of the earthquakes. Reisenberg keeps more. And nearest neighbor and Robert, the mean of Robert, are fairly similar to each other. So we can decluster. We could test whether these things are truly Poissonian. But more importantly, what do these different methods do to hazard? Well, hazard will come a lot from the b-value, from the magnitude frequency distribution. So here we have magnitudes from 0 up to 7. The full catalog is given here by these black dots, and its fit is given by the black line. And the only one I want to point out is going to be Gardner-Knopfloff. And the reason I'm going to point it out is notice the full catalog had a b-value of 0.9. Gardner-Knopfloff gave a much lower b-value of 0.8, much bigger difference than the uncertainties. Reisenberg, nearest neighbor, and Robert all gave things very close to 0.9 with an uncertainty. So notice the purple line, which is Gardner-Knopfloff. The purple dashed line here eventually crosses around magnitude 5.3 or so and starts predicting too many large earthquakes. And that's going to affect our estimates of hazard. Okay, so now we're going to move from declustering to hazard. And this is, of course, the seminal paper on probabilistic seismic hazard analysis by Alan Cornell. What did he do in this paper? he made some assumptions. He said within a given source, whether it's a fault or a regional source, the earthquakes are equally likely. That there's a Gutenberg-Richter distribution of magnitudes and Poissonian time behavior. The analytic solution, he came up with an analytic solution. Remember, this is 1968. Analytic solutions were great because you could explore different parameters. Computers were very slow. So it was very good to have a simple formula. And he showed that you could overcome the first two assumptions. The constant rate for the Poisson process can be overcome by dividing time into different periods of constant rate. But that he said breaking the independent event assumption bears a heavy penalty. So that was a problem. Notice in this paper, he does not discuss declustering, as I said before, because there was no declustering method that worked. Instead, he pointed to studies of data on larger earthquakes that said that, for a few large earthquakes, we can't reject the Poisson null hypothesis. So essentially, he was going to go into the pretending mode. We're going to pretend the data is Poisson. And in the meantime, somehow, declustering became commonplace for PSHA. I'll point out now we have fast computers. We could probably simulate catalogs. We could simulate the hazard and do away with all of this math. And sometimes we want to look at correlated hazard, such as, if one bridge breaks, will the other bridge that crosses the same body of water break? So here's the question. Should we leave the aftershocks in or do temporal correlations? But for the moment, I'm just going to look at the impacts of the different declustering methods on hazard. Okay, so here are maps of earthquake rates in the San Francisco Bay Area for 5 methods: Gardner-Knopf declustering, Reisenberg, nearest neighbor, the best fitting ETOS parameters, and taking into account uncertainty. What we see is that, of course, as usual, Gardner-Knopf has the least red colors. It has the lowest rate. Reisenberg, nearest neighbor, Reisenberg has the most, nearest neighbor, ETOS, Emily, and especially Robert seem very similar to each other. I'm going to skip that slide. So now I'm going to take these rates and the B values that are associated with each of these catalogs, if that's what gets done in most PSHA, and I'm going to estimate the hazard. So these are maps of the ground motion, the peak ground acceleration likely to be exceeded with 1% chance in 1 year for each of these methods. So notice that Gardner and Knopf, which had the lowest earthquake rates, now has the highest hazard. It has the highest ground motions that are likely to have a 1% chance of being exceeded in a period of time of 1 year. Why does that happen? Well, it happens because of the B value. So biasing the B value in declustering is something that I worry about a lot in how we do seismic hazard assessment. I think we should be switching to, and I believe at the USGS, we are in the process of switching to methods that don't change the B value so much. Whether that will turn out to be Reisenberg and nearest neighbor, or whether we'll move to Robert is still to be seen as we work on these things. Even today, we had a meeting discussing this. There's another possibility to use to end our discussion of PSHA. And this is a paper by Warner Marzocchi and Tironi, published in 2014, looking at ground motions that exceed 10% in 50 years. This is a standard sort of level of PSHA to look at in Italy. So if you apply Gardner-Knopf declustering, this is what the ground motions look like. Now, of course, another end member we could do is we could leave all the earthquakes in. So this is not declustering the catalog at all, which changes the B value, but probably doubles the number of earthquakes and doubles the earthquake rates. And we see that we get a lot more hazard, a lot more red areas, high ground motions. But in a lot of these areas like here, this is because, or actually up here also, this is because of a recent large aftershock sequence. So what happens is we distort the space, and we're biased to saying where we've already had a big earthquake and a lot of aftershocks, we're going to get more earthquakes over 50 years. And that may not be the best assumption over 50 years. Over a year, 2 years, 5 years, yes. But over 50 years, some other area may have a big earthquake. What they actually suggested was taking the earthquake rate estimated here and then just scaling it up to the full rate of the catalog. So this decreases the impact of the large aftershock sequence in a spatial sense, but keeps the total number of earthquakes happening in the region over the next 50 years the same as we've seen in the previous period of time. I think this is very good. And actually, we are actually next year going to issue a hazard map that will very likely include this this method in it. We've under discussion again today at a meeting. So this will actually be a map for Hawaii. Will be the first place we do it. Okay, going to end with one last thing, the effect of clustering on prediction testing. So this is the last place where sometimes pretending that you have a Poisson process can be a big problem. So this was a paper by some people in Russia, Rulitov and Marenko, on the concept of radio wave earthquake forecasting. And I got drawn into testing this method for some intergovernmental negotiations. So the idea they have is there was these Omega signals. Omega was an old navigation system with very large, very low frequency land transmitters that would then be received on, say, a ship or somewhere at a station that they operated on land. And you could, by measuring the times and the phases of VLF from different places, it was like GPS, but without satellites, and much less sophisticated. And there was a daily cycle in the way the VLF behaved, and that's because this is travels in a waveguide up to the ionosphere, and the height of the ionosphere varies daily due to solar heating. And they noticed that sometimes there were anomalies in the daily cycle. This is from 2 different transmitters. You can see only one of them has an anomaly. And then along the path from Reunion Island to Omsk, where the receiver was, there was then an earthquake. So they thought maybe these anomalies, some behavior of the ionosphere predicts earthquakes. They did some statistics. This is the time between the ionosphere, the anomalies and the earthquakes. And so they tried different times, and they found that for particular times, this had a very low probability. And I got asked to look at this. So this made them think they had a good prediction method. And when I looked at it, I realized that they were doing a Poisson process. They were using a Poisson model to produce these probabilities. And when we sat down in Moscow and we talked about this, I said, yeah, we knew that could be a problem, but we didn't know what else to do. And so it sort of became my job to try to figure something out. So again, here we had the receiver in Omsk, a transmitter in Liberia, crossing these trying to predict these earthquakes here, and this other path trying to predict these earthquakes. So we have time series. We have time going on here. We have earthquakes occurring on each path. The height of each bar is related to the magnitude. We have when there were anomalies seen in the diurnal behavior of the VLF transmission, the phase velocity of the transmission. And then these are data dropouts. The station in Omsk was not very reliable, and so we had to account for data dropouts. And so the question is, and it's hard to see from here, are these anomalies really related to the earthquakes? So what we do is we have a timeline, we have anomalies, we have dropouts, and we have some shift, the minimum time to an earthquake, and then some duration on which we think there might be an earthquake, and that gives us a prediction window. And then we see how many earthquakes happen during the window, and then we have to ignore some times where, due to the dropouts, we just don't know what's going on. So what they did, and what we'll do, and I did also, was optimize the predictive power by varying shift and duration. So this is a retrospective fitting of attempting to predict earthquakes. Then we did it again for many simulated random earthquake catalogs. They did it for Poisson catalogs. I'll do it for a few types. And we compute the probability that the observed quakes are predicted better than the random quakes. So this is a dangerous thing we do, is retrospective optimization. And this is sometimes called there's a fallacy that has to do with, what if the king shoots arrows at a wall, and then later he orders someone to draw circles around them? And so it looks like the king shoots, very well. But because Dave Jackson loves this analogy at UCLA, but because someone has painted the targets after the arrows were shot retrospectively, this proves nothing. Not only that, if the data are clustered, if the king tends to shoot randomly but in clusters, the person painting the targets has less work to do. It's easier to paint targets around these clusters of arrows than it was to paste them around truly random shooting. And this is why we have to worry about whether the earthquakes are Poisson or not. Okay, so here's a search. So this is the duration of the windows we predict earthquakes in, from 0 to 120 hours. This is the time between the anomalies and the earthquake windows for the two paths. If it's red, then we see that there were more earthquakes than expected in the windows, and we find the best one, which here had 0.024 events per hour more than in some of the blue windows. And then we do the same thing for Omsk, and we find the highest point. And then we keep doing this over and over again for simulated catalog. So I'm just going to look here at the Liberia to Omsk path. So the real value here is we got 0.024 more earthquakes per hour in the prediction windows when we picked these parameters. A very short window, about 54, 2 days later than the anomaly. And if I do Poisson simulated catalogs, I get a distribution. So I do it many times. I get a distribution of how well I can fit the data. And we find that there's only 6% of the time do we do better than the real data. So that's getting pretty close to 95% confidence. And it was even a little better on the other path. So so the first thing was inner event times drawn from an exponential, Poisson. Next, I drew inner event times drawn from the observed data. So basically the observed data is aftershocks. So now I'm going to have more short intervals, more clustering. And if I do it again with the empirical inner event times, but no autocorrelation, I now get a probability that 13% of the time the fake data does better. I'm better at predicting the fake data 13% of the time than I am at the real data. That is not 95% significant. And then, as we mentioned before, non-Poisson processes both have differences in the inner event time distribution, but also in autocorrelation. So now I do something called a first order autocorrelation. So if one short inner event time happens, it's more likely to be followed by another one. This is just a very little bit of autocorrelation. And now we have a 0.18% chance, 18% chance that my random data can be predicted better than real data. And so what we see is that the more clustering we put in our model, the prediction method looks worse and worse. And I could put even more clustering in, but we were done sort of at this point because we'd shown that the method really wasn't doing better than random. It was only doing better than random if we thought it was a Poisson, we thought the data and earthquakes were Poisson, and they're not. So just to go over this, optimization and prediction tests, is varying parameters. It's in a search for extreme behavior. And clustering makes the behaviorless optimization by data fitting less stable. And so we're more likely to find extreme behavior, which are better predictions. Clustering exists in real earthquakes, and so therefore, if we ignore it, it'll contribute to what appear to be better predictions. And so a lack of clustering in the simulated catalogs will lead to overestimating statistical significance. And therefore, if you're going to test earthquake predictions made on data that included aftershocks, you better include clustering in your simulated catalog. So taking into account clustering is very important for testing earthquake predictions. Okay, 2 more slides. So in physics, there's often a joke that they say, well, let's assume a spherical cow. And so, of course, this would be a spherical cow. Doesn't really look very much like a real cow. And I would say that the Poisson assumption is the spherical cow of statistical seismology. Let's assume the earthquakes are statistical. And I would say it's useful. We can do a lot of calculations, but we must treat it with caution. And I'm going to point out 2 things now. This is near Parkfield. I can tell you that the San Andreas fault is here. And we can see 2 things. One, the cows are not spherical. And the other thing is that they're clustered. And we are servicing the station, and I can tell you the San Andreas fault is right behind, probably running underneath our truck. And not only that, the cows were clustering along the San Andreas fault. However, the cows were not clustering because of the fault. The cows were clustering because they thought we were going to feed them. And so the half hour we were fixing and monitoring the station, the cows just stood there, hoping we were going to pull out some hay. So that's the end of my talk tonight. I hope you understand the good and bad of the Poisson distribution. We will all continue to use it in ways, but we should treat it with some care. Thank you.
Thank you very much, sir, for your talk. You have beautifully explained about the Poisson process and Poisson distribution on occurrence of earthquakes with case studies. Now, let me invite Professor J.R. Kyle for his opinion. About the Professor J.R. Kyle.
Thank you, Shantanu. I think today Dr. Michael has, he has made us speechless. Your lecture is so educative, so enlightening. You have clear from grassroots to the whole process, the Poisson behavior, the Poisson process, and the declustering methods, and everything. I think you have cleared for all of us, and particularly those who are budding scientists, young people. I think for them, I think it's a tremendous platform, and where you have really taught some thousands of students with basic things and how we should do research, and it was fantastic in one word. I hope there will be a lot of questions. Thank you, Michael. It was a wonderful lecture today. Thank you so much. Over to Shantanu, please.
Thank you very much, sir, for your comments. Now, may I request our co-session chairperson, Dr. Saurabh Barua, for his words.
Yeah, I have no word. Actually, I was just the first lecture, it was in my heart. And this second lecture, I have to repeatedly see, watch, understand, and learn and replicate to the field, because it is in YouTube. I'll go through it number of times. That's the request I wish to make to the budding scientists as well. Once again, on behalf of CSIR Northeast Institute of Science and Technology, we thank you a lot, sir, for taking our invitation. And I hope your collaboration with Dr. Shantanu, convener, will continue and groom in a better perspective. Thank you so much, sir. That's what I wanted to convey.
Thank you very much. Thank you very much, sir. Now, may I request Mr. Prasidjo for question and answer sessions. About Mr. Prasidjo.
Okay, sir. The first question is, can you please suggest a comprehensive book on earthquake statistics?
It's an excellent question. And so quite a number of years ago, I suggested to Stefan Wiemer that he write this book. And he decided to say no. And he said no because he said books are outdated. And so what we started, and we have not added to it lately, it's sometimes hard to get people to write chapters, including myself, is the website Corsa, CORSSA.org. So the Community Online Resource for Statistical Seismicity Analysis. And I gave a reference to a paper there, I believe, in the suggested reading. And there are other papers there, and hopefully we will get back to adding chapters there. And one of the good things is we can update it. So for instance, there is a very good paper there on declustering methods by Thomas von Stiefhout. And but maybe someday we will add Robert. So Corsa is not for new research, it is review papers and tutorials. And hopefully we'll keep adding to it because there is no good book. But fortunately, Corsa is open access, so it is free.
Thank you, sir. Next question, please.
Would you please explain the clustering of catalog?
So I see this question was put in a little while ago, and I talked for a while after that, so maybe I explained some of it. Catalog declustering is, there's quite a number of methods, I believe, explained in the Corsa website. And I think it's important to explore different ones and see how they behave with your data. And I'd also say, try different parameters. Just as Gardner and Knophoff asked us in 1974, don't just use the default parameters that someone sent with their code. Change the sizes of the circles to fit your region. Change the lengths of things to fit your region. But I too long to explain it in more than I did tonight. But I would very much say go read the Corsa paper.
Yes, sir. Where it stands, the Poisson distribution for triggered seismicity and stress transfer Coulomb, please explain.
For triggered seismicity. So obviously triggered seismicity and, in space, the Coulomb distribution would violate the Poisson distribution, because if one earthquake triggers another, they're not independent of each other. So we generally use those things like triggered seismicity in Coulomb in aftershock forecasting, and those are what we call sometimes a non-homogeneous Poisson process. So it is a Poisson process in a short period of time, it may be instantaneously, but that changes with time. So homogeneous is a constant rate, non-homogeneous is a changing rate. So we do still have some, basically in those cases, we can't really use, say, the data is Poisson itself.
Okay, sir. The next question is, how do we determine the number of foreshock and aftershock within the space-time window generated from a magnitude of earthquake?
Right. So I think, the basic way we do this is we look at old data. And so we would say, we go around the world for, say, magnitude, 6 and greater earthquakes, and we see, how many aftershocks did they have within some distance for, say, the first week or the first month. And we build up experience, and then we can fit equations to that, like the modified Amori equation, or an equation, a space equation that we have in space-time ETOS. And so there's a question, this is really an empirical thing, but we also then want to make sure it makes sense. So for instance, in space, we won't want the distance to be shorter than the fault length for an earthquake of magnitude 6, if we're looking at magnitude 6 main shocks. And so we want to try to see if we can make physical sense of the empirical distributions we work out.
Okay, sir. The next question is, foreshocks and aftershocks also contributing in elastic energy and seismic ground motion, then why do you need to do clustering while calculating B value and seismic hazard assessment studies?
Excellent question. So for a long time, I thought that maybe all earthquake engineers and engineering seismologists thought we should really only look at the main shocks. And really, as I said, Alan Cornell didn't say to decluster the catalog. He just said to pretend it's Poisson. And he did that because computers were slow. And then a few years ago, I was at a meeting with Ken Campbell, who is a very noted earthquake engineering seismologist. And he said, no, engineers are always asking me why we throw out the aftershocks. So I think we should be finding ways to put them back in. I think the Marzocchi and Tironi method suggests a way to put the aftershocks back in. We have some full simulation methods that are very expensive computationally. They require supercomputers and tens of thousands of dollars to run, so that's probably not very effective. But I think we have to develop smarter methods that are efficient and keep some of the character in. I agree, we need to keep them in. The one reason to decluster, though, is when we try to get the background rate of earthquakes, and then we add aftershock on top of that. If we imagine an area and we only have, say, 20 years of observations, and we have one big aftershock sequence, and then we just spatially smooth, as we do for spatially smooth seismicity in probabilistic seismic hazard analysis, we would say that's the most dangerous area. But maybe it's not. Maybe it's just in 20 years the place that happened to have a big earthquake. So I think for getting the spatial pattern of main shocks, we should decluster, but then we should doing the calculations aftershocks back to all of the possible main shocks, not just the ones that happen. And we're still working on how to do that.
Okay, sir. So I think this is the last question. Can you explain the clustering pattern in Southern California?
Can I explain the clustering pattern? That's a hard one. Can I ask, there's actually one other here that I want to answer. I see. It says Robert seems to be retaining swarms and time clusters. Is that so? And very good eye, I'm going to say. It does not completely knock out there's an aftershock sequence in 2014 in the data I showed, and the South Napa earthquake. And more importantly, there was actually a swarm in the East Bay in 2015 that it does not knock out. Why doesn't it knock that out? It doesn't knock it out because a swarm is a change in the background rate. And so when we do the ETOS declustering, if you go back to the equation, the background rate varies in space, but not in time. And so Robert has a little bit of a problem with swarms. And the question is, do we want to get rid of the swarms entirely or not? And but that is why we haven't applied it to a seismic hazard map yet. One of the reasons. So it's a new method. I think it has promise, but good eye. We have to work on those things. I believe in the paper we honestly discuss that. The clustering pattern in Southern California. There's many aspects to the clustering of earthquakes in Southern California. The parameters for clustering, the productivity of aftershock sequences are higher in some areas than others. That may be related. Some people feel the heat flow, where some of the hotter areas tend to have more productive aftershock sequences. That did a good job of explaining the 2019 Ridgecrest earthquake had a lot of aftershocks. Yeah, we also get swarms near the Salton Sea. I think I discussed that a little bit in my previous talk, perhaps. I gave a couple of talks in between, so I'm having trouble remembering. But there's some geothermal areas that have swarms of earthquakes in Southern California. So Southern California is very complicated because we have both strike-slip motion there, and we have thrusting that builds mountain ranges, partially because the San Andreas Fault is bent and has trouble moving around the corner. And we have geothermal areas. So the clustering pattern in Southern California, that strikes me as at least an hour-long lecture. So, but good to read papers on that. And there's a lot of complexity there.
Okay, sir. I think that's all.
So thank you very much for your time and excellent presentation. I hope you will continue encouraging us in this way in near future too. Now may I invite Mr. Prasidjo for vote of thanks. Over to Mr. Prasidjo.
Thank you, sir. Good morning, respected dignitaries. I, Prasidjo Boythakur, on behalf of CSIR NIST and the entire organizing committee of this international virtual workshop on global seismology and tectonics, convey my sincere thanks to Professor Andrew Michael, sir, for such an informative and descriptive talk. It was an honor to have you on board us today, and your lecture has showered tremendous knowledge upon us. And thank you so much for sparing some time from your busy schedule and enlightening us with such an amazing talk, sir. Thank you, sir. My sincere gratitude goes to our respected director, sir, Professor G. Narahari Shastriji, for giving us the necessary permission to conduct this international workshop. My sincere thanks goes to the chairperson of the session, Professor J.R. Kayal, sir, the former Deputy General GSI, and the co-chairperson of this session, Dr. Saurabh Barua, sir, Chief Scientist, CSIR NIST, for their continuous support and guidance in each and every step of this successful completion of this international workshop. Nevertheless, my sincere gratitude goes to the convener, Dr. Santanu Barua, sir, Senior Scientist, CSIR NIST, for giving us such an amazing and wonderful platform to interact with some prominent figures in the field of international seismology. At last but not the least, I thank all the participants across the globe for their active participation and the entire organizing committee for their tremendous effort and hard work to make this virtual workshop a success. Thank you all. Love from India.